Nuclear power. It will be useful to examine the first occasion on which a controlled chain reaction took place. The world's first controlled chain reaction using uranium fuel took place on the 2nd of December 1942 under the racquet court at Stagg Field in the University of Chicago. And it was carried out by an Italian called Enrico Fermi and his team. We're obviously talking neutrons here. The neutron was discovered by Sir James Chadwick, one of Rutherford's men in Cambridge in 1932. And in the 30s, Enrico Fermi was working in the physics department at the University of Rome. And he became very interested in neutrons, and he was one of these very unusual men who was gifted both as a theoretician and as an experimentalist. And he conducted many experiments at the University of Rome, bombarding targets with beams of neutrons. But he realized that the energy of the beam of neutrons was very important, and he devised ways of controlling beams of neutrons to get exactly the energy level that he needed. And what he found was that if you pass a beam of neutrons through a sheet or a block of paraffin wax, you can slow the neutrons down. Now, he took it further than that. If you wanted a certain neutron beam energy, he could then tell you exactly how many millimeters or how many centimeters of paraffin wax you needed to pass the beam through to get that level of energy. So he studied neutron beams and their behavior and properties, and when the Manhattan Project was first set up, one of the first objectives was to see whether it would be possible to achieve a controlled chain reaction. And of course, Enrico Fermi was one of the first people to be recruited by Oppenheimer, and he set about this work in the Mantle Lab in Chicago University. And paraffin wax is a hydrocarbon. It's got carbon atoms and hydrogen atoms. It's just the right sort of material for moderating neutrons, that is to say, slowing them down. We can also use water, H2O. We can also use carbon, graphite. And Fermi ordered something like 200 to 250 cubic meters of graphite blocks, carbon blocks, all machined to a regular size, like a big pile of building bricks. And he began to build the world's first atomic pile under the racquet court in Chicago. And of course, it's like, it ended up being a structure sort of 6 or 7 meters long by 6 or 7 meters wide by 6 or 7 meters high. And at the center of it, he had holes drilled through the carbon blocks so that the fuel elements could be put inside. Now, we've talked about uranium having two isotopes, and 235 is the really fissile one. 238 is much less active. But Fermi believed that by using slow neutrons, he could induce a chain reaction in uranium-238. And at the time, most, as I say, if you dig uranium up out of the ground, most of it is 238. And at that time, they didn't have a means of enriching it. So Fermi decided to use 238 and as the fuel, and he began to build this atomic pile. He called it a pile because it literally was a pile of carbon blocks. The term nuclear reactor didn't come into use until the early 1950s. Anyway, he built this pile, and as it got higher, he started drilling the holes. And of course, at the center of this great mass of carbon was the area where the reaction would happen, and the fuel elements were put into holes in the blocks. And Fermi had calculated the distance between the fuel elements and how many would be required. And right at the center, he placed a neutron counter so that he could measure the neutron emissions on a continuous basis. And he superintended the building of this, and on the morning of the 2nd of December 1942, 1942, he realised that they'd reached the crucial stage where they were adding the fuel elements that would actually make the reaction go critical. In other words, you would achieve a sustained reaction. And he invited about 20 people to come down to the room to observe this. He was so confident of success. And there he was with his slide rule in one hand doing the calculations and telling him where to put the blocks and the stuff in the other. And sure enough, they could all hear this click, clickety-clack, clickety-clack, clickety-clack of the neutron counter. And suddenly the speeding of the clickety-clack increased until it became a steady roar. And Fermi said, "Gentlemen, the reactor has just gone critical." In other words, they'd achieved a controlled chain reaction. That was the first time it happened. It was a big step forward because it meant that the knowledge of the neutron, it's one thing to know something as being, if you like, theoretically possible, but you have to actually do it to prove that your understanding is such that you really do know what's going on. And this experiment was very successful. It proved two things. Firstly, that controlled chain reaction was possible using uranium-238. And the second thing it proved, which they didn't find out until they'd run this thing for a bit, they analysed the products of the fission reactions and found that they had actually produced in this atomic pile a certain amount of plutonium-239. Now, plutonium-239 is also a highly fissile material, eminently suitable for making atomic bombs. At that point, they knew that it was a man-made element. If ever there was any plutonium in the world, and there may have been, it had all, by the time 1942 came around, all this had decomposed years ago and decayed, and there is none naturally occurring in the world today. It's fairly stable, it has a long half-life, and it is eminently suitable for making weapons. So this experiment had proved two things which are very important for the future of nuclear energy. Controlled chain reaction is possible, and also how to produce uranium-235, which is also fissile. Not only can it be used for bombs, but it can also be used to generate nuclear power for peaceful purposes as well. So that was the first chain reaction in this so-called atomic pile. And of course, during the war, everybody bent their energies towards the creation of weapons. Now, after the war, we know that the Russians were attempting to build their first weapon, which they did in August 1949. The British were also working on their weapon, which they succeeded in detonating in October 1952. But work went on independently to harness nuclear energy for peaceful purposes. Now, the first country that fed, if you like, nuclear-generated electricity into the national grid was Russia. They had a small reactor at a place called Obninsk in the Soviet Union, and early in 1954, they fed power into their national grid. A few months later, the Americans also fed power into their national grid from a similarly small nuclear reactor. The term reactor had come into use at this time because people had started to design entities specifically for controlling nuclear fission. Fermi's atomic pile was literally that. It was an experimental lash-up. The first proper nuclear power station opened in Britain 2 years later in 1956. Now, this was quite different from what the Russians or the Americans had done. This was a full-blown, large nuclear power station capable of feeding megawatts of power into the national grid. So that's the early history. Now, what lines of development went on with designing these nuclear reactors? There were two principal lines of work, one of which originated from the Chicago experiment. That is to say, designers built their reactors using graphite, carbon, as the moderator. You need slow neutrons to do this. You don't want fast neutrons, so you need the carbon to slow the neutrons down to moderate their speed. And that was one approach that was taken. Now, I mentioned that water could also be used as a moderator, and another line of development went along using water. Now, the thing about water is we can use it as a coolant and as a moderator, but when it gets to 100 degrees Celsius, it boils and you get steam. Now, steam can't act as a coolant, it's a gas in the same way. Gases can be used as coolants, but water is less effective once it's boiled. Now, what physicists also knew was if you increase the pressure of the water, you ramp the pressure up very significantly, you can delay its boiling, you can raise its boiling temperature well above 100 Celsius, and it will continue to be liquid. So this was the concept of the pressurized water reactor, the PWR, where water is used as a moderator and coolant, and the water is in a special high pressure circuit, which means that it stays liquid. I've mentioned the difference in size between the American reactors and the first British reactor at Calder Hall, which fed power into the national grid. Now, the Calder Hall reactor was a design using graphite moderators. Besides creating reactors to generate power for civilian purposes, the military realized that controlled reactions could be used in other ways that were very useful. Submarine warfare had proved to be very important in World War II, and of course the problem with World War II submarines, they're powered by diesel engines, which means they have to come to the surface frequently, and once they're submerged you can only use the electric motors, which was a sort of limitation on their use. And both the Russians and the Americans realized that if they could build small nuclear reactors, they could put them into their submarines, and then in principle the submarine could remain submerged for days, weeks, and even months on end without the need to surface. Clearly this was militarily a big plus. Also, about the same time, the Americans were contemplating building a fleet of very large aircraft carriers, and of course again, capital ships have always been tied to, first of all, coaling stations. They used to have to visit a coaling station 100 years ago to stock up with coal, but then the Royal Navy pioneered the use of oil-fired turbines early in the 20th century, which made things much more easy. You could refuel at sea from a supply ship. But even better still would be a capital ship that didn't need to be supplied at all. So in other words, if you could build a nuclear reactor big enough and powerful enough to generate the power, you can power one of these 100,000-ton aircraft carriers using nuclear power. Now, the reactors for use in submarines and aircraft carriers are typically pressurized water reactors, small versions, and the Russians certainly developed those for submarines and so on, and capital ships. But the graphite moderator design tended to be used in larger reactors, used for generating megawatts of power for feeding into national grid situations. The Russians adopted the graphite moderator principle for their nuclear power stations. Many parts of Russia at that time, after the Second World War, had no electricity and had never had any electricity. And they had a very ambitious plan to build large nuclear reactors capable of putting each one generating 1,000 megawatts for the national grid. The Russians had some very gifted reactor designers, including Anatoly Alexandrov, another guy called Nikolai Dolezhal. And Alexandrov favoured graphite-moderated reactors housed inside steel-reinforced concrete vessels. So these were huge cylindrical vessels with a cap at the top and another cap at the bottom. And they contained a large graphite core with holes going through, into which the fuel rods were put, and the moderators and so on. The Americans fairly quickly went over to the building of pressurized water reactors for these very large reactors themselves. They didn't go down the concrete graphite route. The thing with building very large steel PWRs is you're faced with the problem of welding steel plate sort of 100, 150 millimeters thick. You're faced with the same problem building submarine hulls that were capable of submerging 1,000 meters as well. And unless you've got the technology to weld steel plate that thick, but even more importantly, unless you've got the technology to survey the welds after you've done it for quality, you're very unwise to go down that route, because if they're called pressurized water reactors because they have to contain water under pressure. If there's a burst or an explosion, you've got a very serious problem on your hands. So unless you can rely absolutely on the integrity of the welds, you've got a problem. Now, so Russia eschewed that solution. The concrete solution was a simpler one. Concrete is a good material for shielding nuclear reactors because you can add graded lead shot to the concrete mix as part of the aggregate, and it will be very effective then at containing the fast neutrons, the neutrons that are emitted, and shielding the crew from radioactive damage. So they went in for this design, this Rbmk design, which was, I suppose, typical of the design that was used at Chernobyl. And for many years it was very successful, and the Russians were building. Chernobyl was actually going to be the world's largest nuclear power station. The one that exploded was reactor vessel number 4. They were building reactors 5 and 6 when it happened, and the land was marked out for reactors 7 and 8. So this plant would have eventually fed into the Russian power system something like 8 gigawatts of power, which is huge. It would have been the world's biggest power station. So there were these two approaches, the PWR design and the graphite moderated design, and that's how things were through the sort of 60s and 70s. And then two occurrences dealt a severe blow to the development of nuclear power, namely the 3 Mile Island incident in Harrisburg, Virginia in America, and of course a year or two later the Chernobyl disaster. The Russians sort of rubbed their hands in glee. These capitalists are so interested in money, they don't think about safety. Well, there was a little bit of truth in that, because the Power Authority in Virginia, if they could get this plant running by the end of 1979, they stood to save 1 year's tax on their revenues. And so they were actually cutting corners a little bit when they were commissioning this plant. And there was an incident, I'm not sure exactly what happened, but there was a bit of a partial heavy nuclear flux and only a partial meltdown, and there was a small emission of radioactive material, and they shut the Harrisburg plant down, and it stayed shut down for quite a while. At that time, there were many contracts signed for the building of more nuclear power plants in the United States. And as a result of the 3 Mile Island thing, these contracts were all pretty well cancelled. Now, the Russians ploughed on, and while the Rbmk Design reactor was okay, it didn't have the same kind of fail-safe features that the Western reactors did. If there are various safety features that you need, your plant relies on electric power, and if for any reason this power is cut, the problem of inserting control rods, which you need to insert to stop the reaction, or the problem of removing the fuel rods, can require power. But if you design the reactor correctly, it's possible to have the fuel rods aligned vertically, and if there is a failure, then you just open some little doors, and the control rods can actually fall out under their own weight into the cooling pond under the reactor. Once fuel rods are removed from a reactor, then 90% of the activity stops, because they're no longer interacting with each other and causing fission. However, they are still radioactive, and they will still produce 9 or 10% of the activity they did in the reactor, just due to spontaneous radioactive disintegration. So if you put them into a cooling pond, they will slowly warm the water up. And unless you feed in cooling water to keep the temperature moderate, the end result is that they can boil this water, and then you're in trouble. You can get a meltdown. And so you need power to remove the fuel rods, and you can require power to insert control rods. But again, if you design a reactor, you can let the control rods fall in from above under their own weight again. If triggered by a power cut, they can fall into the necessary slots and control the reactor. Reactors need 2 things. They need moderators, which will slow the neutrons down, and they need control rods for the times when you want to actually shut the reactor down. Control rods don't slow neutrons down, they actually soak them up. And things like cadmium, metal cadmium and boron steel, things like this, are suitable for use as control rods. So the reactor design evolved from Fermi's initial experiment over the next 20 or 30 years down 2 routes: graphite moderator designs, pressurized water designs. Now, at the moment, there are something like 450 nuclear reactors in the world, that sort of order, and I think something like 2/3 of them are PWR design. So the PWR reactor has become very important, but it's a convenient point to draw this initial discussion to a close, the point where Chernobyl and 3 Mile Island caused a real cessation in the building of new power plants, and everybody sort of paused and thought again. Not everybody. The French carried on building nuclear power, and Japanese and 1 or 2 others, but mostly those 2 events dealt a blow to the nuclear power industry, which set it back. It's now reviving again, and the ideas are being taken forward, but we can call a halt on this first discussion at that particular point at the end of the 70s and beginning of the early 80s.